Who are you talking to?
Facebook.
You're talking to Facebook? Mark Zuckerberg.
Did you make the weekend?
It did.
Can I get some points? Something hints?
Yes. One question on mechanics,
Wow.
one question on electricity, and one question on waves.
You said yesterday.
Still true.
Exactly.
Is it what?
And more.
More hints.
More.
There will be section A and section B. What? No? Not this?
Which example of which question?
Oh, that's, no, I couldn't tell you that.
Which one is
Topic. I know the topic.
Maybe there might be a Kirchhoff question. And maybe there might be a Newton question.
What music?
Many Newtons.
Many apples.
Many apples. Okay. Continue. Reflection, diffraction, and refraction. Reflection, diffraction, refraction. Yes. Fraction, fraction. Okay. There's a lot. Right, so firstly, what's reflection? So reflection is a change in a direction of a wave so that the wave comes back from where it came. Most common examples include reflection of light against a mirror, sound and water against a wall. So reflection, you know what reflection is. The light comes back to the source. Well, it doesn't have to come back to the source, it comes back to the medium it came from. And there is an example of reflection.
But then, if it goes back to the medium it came from, it has to be perpendicular to the mirror, right?
No, it could make a bit of an angle.
But if it was to, from an angle, it go like that, right?
So this medium here is the air, and the second medium is the silver glass.
Oh,
So
it goes back into the air?
Yes, is essentially it, yeah. Okay. That's reflection. Next was
No.
yeah.
Diffraction.
So one thing I find strange about the physics course is that it's broken up into 6 parts, but each part is very different in length. So the mechanics part was really big, wasn't it? Mechanics. But the wave part is really small, really small. Because so far we're on lesson number 3 for waves, and I don't feel like we've done that much, except for one formula, you know. So the waves, I like it in the exam as a question, but students don't like the wave question in the exam because too many words. Yeah, too many words. Yeah. Less formula, too many words. Okay, next. So that's reflection. Diffraction occurs when the wave bends around small obstacles or when the wave spreads out after it passes through a small opening. So if you remember from the active listening, this is what's happening here. When the wave passes through a small gap, it spreads out. So here's a picture of it here. So maybe this is like an ocean wave. So when the ocean wave passes through a gap, it spreads out. But if the gap is really small, the wave spreads out more. So this is called diffraction. The wave spreading out as it passes through a gap. Yeah? You don't have to draw the pictures. I just drew the put in the pictures to help you understand the definition. You can draw it if you want.
In this case, pictures are more easier to understand. Definitions are complicated.
Continue. Yes. Reflection. So you have the air, and the light moves through the air, and then it hits something and comes back to the air. So it's a change in the direction of a wave. Boundary, you see here boundary? Yeah, that's the mirror. And then the light comes in, hits the boundary, and then comes back. Yeah. So it says here, what's this? Boundary between two different mediums. So air is one medium, and the mirror is the second medium. Yeah. Mirror. Yeah. Good. And so it doesn't go into the second medium, it comes back to the first medium. Yeah. Okay, continue. So we've done reflection, diffraction, and refraction. So refraction is a change in the direction of a wave caused by a change in the wave's speed. Refraction is seen most often when a wave passes from one medium to a different medium. So here's an example here. So look, this here is air. This here is glass. When the light goes from the air to the glass, it changes its direction. And then when it goes from the glass to the air, it changes its direction again. This is called refraction. This change when you pass through a medium is called refraction.
Also like air to water.
Yeah, air to water as well, yeah. Yeah. Or even warm air to cold air as well. Okay?
No.
No, not okay.
Is it the glass or mirror?
That's glass. Changes its direction when it goes through the glass, yeah. And then when it, yeah, when it goes from the glass to the air, it changes again.
Change back or another?
Oh no, it could be a different angle, yeah. Yeah, that's true. I don't think this is the same as this. Well,
Is it?
no, actually, maybe it is the same. Yeah, maybe it is the same. I don't know. I'll have to calculate it. We'll do a question like this. Okay, next. Right, so some materials will allow light to pass through it more freely than others. You know, you don't have to write this down. So you know, for example, it's very easy for light to travel through empty space. In fact, it's completely easy. It's a little bit more difficult for light to travel through air, and then it's more difficult for light to travel through glass. And then for some things it's impossible for the light to travel through. So here the light comes down and it doesn't travel through the table, because if it could travel through the table, I can see through the table. So different materials have a different ability to let the light through it. This is called refractive index. So what we have here is the light is sometimes slowed down when it travels through a material. So remember earlier we said light travels at a speed of c. Remember that? That's only in empty space. When it's traveling through glass or water, it's slowed down. It's always slowed down. So for example, when light moves slower through glass than air. Wait, don't write this down yet. So refractive index is a way to measure how good the material is for the light. And as a formula, it's the speed of light divided by the speed of the light in the material. Now wait, before you write that down, just think for a moment. Will this number be bigger or smaller than this number?
Smaller.
This is always smaller than this number. So this means this is always more than or less than what? What can we say? It's always
More
more
than 1.
than 1. If this is smaller than this, it means in total this is always more than 1. When will it equal 1?
It's a vacuum.
When it's empty space, vacuum, yeah. So this n is always bigger than 1. It's only equal to 1 when it's in empty space. For example, for air, this is nearly 1. It's like 1.001. Okay? But anyways, this is called the refractive index of the material. C is the speed of light, V is the speed of light in that material. Okay, so I want this definition now. And you've done something really bad if your value is negative. Something very bad has happened. Or if it's less than 1, it's also something very bad has happened.
No, the minus represent it's in the opposite direction.
Oh no, much worse than that. Opposite universe, maybe.
Yeah.
Okay? So, if the n is 1, that means it's a vacuum. And if the n is infinity, that means the light has stopped moving. So it's always between 1 and infinity. Let's not look at those cases. Alright, continue. Yeah. Remember, and I think it's worth saying again, remember V equals C only in a vacuum, in empty space. Okay, so Snell's law is a way to calculate the change in direction for the refraction. So do you remember in the picture here, if I go back to it, just back one moment, we would like a way to calculate the angles here. Okay, we want a way to calculate the angles. So there's a law called Snell's law, which allows us to calculate the angles. So, Snell's law, sine angle 1 over sine angle 2 is equal to n2, the index for the second material, divided by the index for the first material. Now, n1 is index for medium 1, n2 is for medium 2. Theta 1 is the angle, very important though, with the normal. I'll explain that in a minute. Sometimes written as I. And theta 2 is the angle on exit, also with the normal, sometimes written as or. Oh look, here's a picture here. So, please note that we measure the angles not with the surface. So like if this is air and this is water, we don't measure the angles at the surface, we measure it at the normal, and the normal is perpendicular to the surface, okay? So please don't make that mistake. So this is like air and this is like water, this is n1, this is n2, this is theta 1 and this is theta 2. So here's Snell's law. So if you know theta 1, n2 and n1, you can know the angle it comes out at, the theta 2. Okay, so Snell's law. And that's not a mistake. It goes 1, 2, and here is 2, 1. So they're opposites. Now look, you don't need to write all of this down if you know it. This is what you need. Okay, you got it? No. Got this now? Oh. The speed of the light in that material. Okay? Not okay. Boundary, surface, border. Continue. Okay.
What is the refractive index table of wood?
Well, light doesn't pass through wood, so
So there is no refractive index.
yeah,
It's infinity.
yeah. Well, it's not even infinity because the light never gets into it, so I don't know.
Mass error.
Mass error, yes. Now, there is a very important case here. Under certain conditions, it's possible to choose an angle so that theta 2 is 90. So if I go back here, I can pick an angle here that makes this angle 90. So for example, I choose an angle here, and this angle comes up to 90. So what would that represent? Almost that, total internal refraction. That you make an angle here, and the light comes out, but if this is 90, it comes across the surface. So it doesn't really enter the second medium. Instead, it hits the top and runs across here. So we can find an angle C that makes the second angle 90. This C is known as the critical angle. Let's find a formula for it. Okay, so let's calculate what the formula might be. So you want theta 1 equals C, theta 2 equals 90. And here's the situation. So this comes in at angle of C. But instead you want theta 2 here to be 90. So Snell's law, sine theta 1 over sine theta 2 equals n2 over n1. What's sine 90? 1. So you have C must equal sine inverse n2 over n1. But please note that this formula only works if the n2 is smaller than the n1, or another way of saying it is that the n1 is bigger than the n2, because remember, you need this number to be less than 1 or you have a problem with the sine inverse. So this is the formula and this is the condition. This only happens when this n is bigger than this n. Okay? So you want the n1 to be bigger than the n2. Then this can happen. Otherwise, it's impossible to happen. Okay, so please note this. So this is how we can calculate the critical angle. Critical angle is the angle you want here to make the second angle 90. So it's what angle you must have here to make the next angle 90. This is called the critical angle. Yeah? Critical. Okay, you got this little proof? It's only a small proof. Yes? Continue? Amanda? Okay. Oh yeah, and actually it should be worth saying here that if your angle is bigger than the critical angle, like here, then what happens, do you think?
It will
Well, something happens, but it goes back. So then it's a reflection. It comes back to the medium. Okay. So this, when this happens, when the light comes back to the medium, it's called total internal refraction. So that's this situation here. Total internal refraction is when it's more than the critical angle, so it comes back. So can you just note this, not definition, this term, total internal refraction. And you can draw it if you want on your picture, if you have a picture. So yeah, you could draw a bigger angle, it comes back. This is called total internal refraction.
All of it
All of it comes back, yeah. Continue? Okay. Total internal refraction. Okay. Continue. Notice in the last lesson you did not see white light. Remember all the colours? Red, orange, yellow, green, blue, indigo, violet, black light. No, not really black light, because then you don't see it, I suppose. Yeah. So you don't have black light, but we didn't see white light. So what's the frequency of white light? And by the way, by white light I mean like the light that comes out of a light bulb. It's white light, mostly. We didn't see it, and that's because there's no... Yes, that's it. There's no frequency for white light. In fact, we have frequencies for red, orange and green. We don't have frequencies for white. Why not? Well, white light is a mixture of all the colours.
So if I was to have like taste of all the colors and put together it becomes like...
Yes, if you have a red and an orange and a yellow and a green and a blue, if you mix all these light colours together, you make a white light.
Light, I mean like taste.
Now, it's different rules for paint though. If you mix all the paint colours together, you get black. So it's different for paint. Anyways, when red, orange and green and so on are added together, the result is white. Now, hang on, you don't need to write all of this down, certainly not. You just need to say white light contains all the colours mixed together. That's enough to write down. Okay? White light is a mixture of all the colours. Okay, can I continue? Yeah. So there's many ways to state Snell's law. So one way was sine theta 1 over sine theta 2 equals n2 over n1. Another way to state it is sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. Therefore, light of different wavelengths will refract differently. This is why white light will produce a rainbow. So I explain that here. Wait, you don't need to write anything just yet. So if you look at Snell's law here, here is white light. So white light has red, orange, yellow, green, blue colours in it. Let's look at the red. So if you look at the red, does it have a big wavelength or a small wavelength compared to the other colours? Red.
The smallest wavelength.
It has a small wavelength, doesn't it? Yeah, small wavelength. So it's lambda 1. What am I saying here? Yeah, so all the different colours here, they all have different wavelengths. So that means what you get out here will be different angles because there's different wavelengths. This is what's happening. All the colours are together here, but when they pass through the glass, because they have different wavelengths, out will come the light at different angles. And this is why the white light gets split into all the colours, because you're making all different theta 2s because of the different wavelengths. Okay. Now you don't actually need this formula in the exam. It's the last formula you need in the exam. But I wanted to explain why the white light changes into the different colours. It is because of the different wavelengths make different angles. So all I need you to do is just to draw this. And you can write here red down to blue. Okay, so just try to draw this. Okay. Did you draw it? Great, okay. Here are the three ways you can state Snell's law. This one we've seen, this one we've seen, and there is another way to state it where you can say that sine theta 1 over sine theta 2 is the speed in the first medium divided by the speed in the second medium. So for the exam, it's usually just the first one, but these are other ways to state Snell's law. And if you want to write the last one down, you can, okay? Sine theta 1 over sine theta 2 equals V1 over V2. Okay, got that? Yep. One use of Snell's law is in a lens. When light enters glass, it will refract. But the lens is curved, this will result in different theta 1s and different thetas 2. However, the lens is carefully made so that the refraction will cause the light to converge. So what I mean here, what happens is, here when the light comes in, the theta 1s are different, yes? But the lens has a special shape so that the theta 2s are so that the light will reach one point. So it's like
Converge.
it converge. It's like the lens has a curved surface, so it means that the theta 1 here and the theta 2 here, they're carefully designed so that the light will reach one point afterwards. And then here the theta 1 is different, so the theta 2 will be different, but the design of the lens means that the angle will make the light also reach one point, okay? So you don't need to write this down, I'm just showing you that one use of Snell's law is to make a lens so that you can control which way the light moves. Okay, let me just think here. We have one question. Okay, we'll do this question and then that will be it. So here we have red light in a glass. Okay. Do you want to write all of this down? You just write down the A part first. We'll do it bit by bit. Okay, so let's have a look at A. So just A, please, and then I'll let you write down B. You got the A? Yep. Okay, let's have a look at A. So, here is the glass, and the red light is moving through the glass. What's the speed of the light here? 2 times 10 to the 8, was it?
Yes.
And what do I ask you for?
Refractive index.
Refractive index. So the N equals C over V. So that would be 3 times 10 to the 8 over 2 times 10 to the 8. So the refractive index for the glass,
1.5.
yeah, is 1.5. Okay. Got that? B part. So, for air, the refractive index is about 1. Red light enters the glass from the air, an angle of 20. So let me draw it before you write it down. So what's happening here is you have the glass, and the red light comes in, and it's at an angle of 20 here, and I want to know what angle it makes in the glass here, okay? So that's the information. You can write or draw. Okay.
No.
Okay.
And first the speed of light, right? Yeah.
Use the first Snell's law, N1, N2.
Mm.
Okay. I can do it? Okay. So here, the N1 equals 1 and the N2 equals 1.5, and this is theta 2. So sine 20 over sine theta 2 equals 1.5 over 1. So we get sine theta 2 equals sine 20 over 1.5. So I get sine theta 2 equals 0.228. So I have theta 2 equals 13.2 degrees.
30, right?
13.
Okay, what is sine 13?
Are you in radian mode?
It's sine 20 over sine x, oh, radian, okay.
Okay. Next part, part C. So in part C, I'll draw what's happening. What's happening here is that in the glass, there's a light, and the red light comes out of the glass, and you want it to hit the glass, but then you want it to come back in, not to leave. So what is this called?
Reflective index.
Yeah, but what's the angle called?
Critical.
The critical angle. That's what you want. So the question is, I'll just write it down, is what is C? The critical angle. Critical angle. So do you remember the formula? What is it? Sine inverse. Now be careful here. N1 is 1.5 and N2 is 1 because it's the other way. So it will be sine inverse 1 over 1.5. So you need to use a theta 1 which is bigger than or equal to 41.8 degrees. If you make it equal to 41.8, it will run across the top. Is that okay?
Bigger than 41.3.
It'll come back, yeah. Is that okay? Yeah. So, questions? Oh, calm down, calm down. The other homework was so short.
How did I get that?
Because you typed it in wrong.
I mean the,
I don't even know what way you typed it in.
yeah.
Okay, close this. Can I close this? Can I close this? Yes?